Alright, today we're going to look at notes number 7, properties from algebra. So you're going to see a lot of familiar properties that we talked about last year in algebra, and you're going to see some that maybe we didn't label as such. You're going to see some that we kind of said, don't worry about these, you'll see them next year in geometry. Well, today it has arrived. So this is the first set of notes that's going to lead into you learning how to do proofs. So we are on notes number 7. Properties from algebra. And this comes out of lesson 2-2. So this is a little bit on the boring side of notes because it's just basically me listing the properties and giving you an example of them. I will verbally highlight important things about them and which ones you will see more often. But just the fact that these will be showing up. So they're break down into two major categories because now we have two ways of talking about things. And the first one is dealing with equality. So these are properties of equality. So that means when you see these properties, equal signs, oops, let me try that again. Equal signs are always going to show up. Now this is not a vocab word, so I'm going to box it. And the first one is probably one of the most used in proofs, and that's the addition property of equality. Now because these have names, I keep doing that. Because these have names, you just need to use the name in a proof. You don't have to write out examples. And I forgot, we need to put stars and underline. So the addition property of equality you used a ton of last year. When you were doing opposite operations, you added the opposite to both sides in order to get something to go from the left side to the right side or to isolate a variable. So you've used this property. So the way that you've seen it looks like this. If A equals B, then A plus C is equal to B plus C. When you are treating both sides of an operation, or an equation, excuse me, by doing the same operation, you have not changed the value of the problem. So that's a common one. But here is a second way of looking at this property, and this is the one that shows up more often in proofs. This deals with, what if you know that A equals B and C equals D? Okay, so we've got two things that we know to be true, and often in properties these come up to be, or in proofs these come up to be not one thing equal to something else, but it's like this angle plus this angle equals the big angle. So we use the angle addition postulate, segment addition postulate in conjunction with this. What this says is that you can take the first thing on the left side of the first equation, A, add it to the first thing on the left side of the second equation, C. That result would be the same as if you took the second thing from the first equation and added it to the second thing from the second equation. So again, this is going to be the one that's going to be the challenge for you, is to try to see when this is relevant in a particular problem. Okay, so that's the addition property of equality. Very, very, very important. Now, we have the subtraction property of equality. And it's very similar to the first of the addition properties of equality starts out the same. If A equals B, then I'm allowed to subtract the same thing from both sides, and it will not affect that equality from remaining in place. So again, I am subtracting the same amount from both sides. Now, we don't usually use the subtraction property because remember we can rename any subtraction problem to an addition problem, so we can add opposites, and if that means we're adding a -3, then we can add a -3. So you don't see this one as much. Really, addition property covers a lot of things. Okay, next, we're just going to go through all our operations here. Multiplication property of equality. So far, this is now our third theorem card we're making. Because properties are can be used in proofs as well. And, you know, again, this goes back to last year and year before. If A equals B, then the product I get when I multiply both sides of the equation by C, the relationship, that value, will stay the same. This one we do see quite a bit shows up in our in proofs, where we're trying to get rid of, let's say, a denominator, or we're trying to get rid of a coefficient of some sort. We can use this property, or, on the next page, its cousin, the division property of equality. Oops, let me change back to black. And I am going to do a proof at the end of this so you can see the application, but it's going to be, if that is the worst start I've ever done. But what I'm going to do a proof of is an algebraic problem that you've done last year, but I'm going to give you justification for all of the steps. Okay, so now we're on division property of equality. And division property deals the same thing that we dealt with last year. And again, if you remember from your teacher talking about what does division look like at this level, we tend not to use the old-fashioned division symbol, and we use the fraction bar for division. So again, we start off with the same hypothesis, if A equals B, so we have some sort of equation where we know the left side and the right side are equal. And now I'm going to add a stipulation. I'm going to introduce a third value, C, but I'm going to specifically tell you that it cannot equal 0. So if that's the case, then A divided by C would be still equal to B divided by C. So just take a moment and think about why would I have to stipulate that C couldn't equal 0. And hopefully you remember, those of you who are in my class, I kind of beat this into your head. You cannot divide by 0. It's the only thing in math you'll never be able to do. I'm going to say ever, like in Taylor Swift. Ooh, and I wrote even. It's one of my daughter's favorite songs. Like ever. Alright, so that will never ever be able to do. So that's why we have to make that stipulation to make sure that somebody will say, hey, I've got a counterexample for your property. What if C equals 0? Then your property doesn't work. So that's why we exempt it, so that we can say the property works. Okay, so there's our basic observation, or 4 operations. So let's deal with some that we talked about last year that you have been using, and probably one of the most popular is the substitution property of equality. We see him a ton in our proofs. Anytime we need to replace something with a value that's equal to our given value, we have to use substitution. Now, substitution, I'm going to give you a little hint, because there's two properties that seem like they're the same, and I'll talk about that second property in a moment. Substitution property of equality is when you are substituting numbers only. Okay, we have another property that looks like substitution, but it's when you are talking about objects. And again, as we get into proofs, this will make more sense. Your job is just at this point really to recognize what property is going on and how it could be used. So this is what it says. All same hypothesis. If A equals B, then either A or B may be substituted nope, that's not it. Substituted. It's a lot of T. Substituted. That's a lot of T's, isn't it? For the other. In any equation or inequality. So basically what this guy is saying is that if I have no two things are equal to each other, they're interchangeable. I can replace one with the other and the second one with the first one. It doesn't matter. Anytime that I want to have something all in terms of the left side, then I can do that because of this idea of substitution. Okay. Another property is the reflexive property. I kind of call him the duh property of equality. And this guy has to do with reflections, and when you look in the mirror you see yourself, and so that's basically what this is saying. It's basically saying that a value, oops, sorry, let me change colors on you. A value is equal to itself. Okay, now that seems stupid. Why would I ever do that? You'll see why in a little bit when we get into our proofs. Okay, let's see, we've got two more, and you used this next property a ton. Some teachers highlight it, some don't. I did, and I verbalized it quite a bit. Symmetric property of equality. So again, any property that says of equality deals with equals only. Okay. So symmetric property says if I have an equation, so if A equals B, then B equals A. So how would this showed up in algebra? Let's say you were solving for a variable, and the variable showed up originally in the equation only on the right side. But protocol, when you're solving an algebra problem, is that you want to know what you're solving for comes first. So you need that variable to show up on the left side. So this property allowed you to pick up the right side of the equation, put it on the left side, take the original left side, put it on the right side. Now your variable is already in the position you needed to be in when you finish with the problem. Same thing happens here in geometry and proofs. You need to make sure that your answer looks exactly the way that you're told it needs to look. All right, we've got one more property of equality, and then we're going to talk about a couple properties of congruence. So transitive property. Of equality. Okay, and this property I like a lot because I think it's just kind of cool. And it basically says if we have two sets of equations that we know to be true, so if A equals B and B equals C. And what you should notice about these two equations is that they have a B in common. So if I took that second equation and wrote it underneath the first equation, like this, there's this overlap with the B's. So our transitive property of equality says, oops, sorry, let me go back to red. Then A equals C. So it's like doing substitution twice is the transitive property. So transitive property and symmetric property, transitive property and substitution property of equality are fairly acceptable to be interchangeable. Now there's some cases that are pure transitive, and there are some cases that are pure substitution. But these two can pretty much float between each other. Now, oh, I forgot, there is one more, and this is the distributive property of equality. The granddaddy for algebra. And this is the one that says if A, no, this one doesn't even get an if. A times the A times the quantity B plus C is equal to AB plus AC. So anytime you need to get rid of parentheses in a problem, we have to use the distributive property of equality. Okay? Alright, so now what we're going to do is talk about properties that just deal with congruence. Now remember the difference between equality and congruence. Equality deals with the measurement of something. Congruence deals with you have a physical object. Okay, so these are now your properties of congruence. And you're going to see properties of congruence. What you're going to see is similar titles to the properties, some of the properties of equality. But what you have to pay attention to, when can you use these, is when you see a congruent symbol in the problem. So our first one is the reflexive property of congruence. And as we go through proofs, you will see me doing how I indicate how I would write this in an actual proof, because I do use abbreviations. So I'm going to go back and add one keyword up here. These are all dealing with objects. So it's not dealing with measurements. So you're going to be seeing congruent symbols here. So basically what it's saying when you have the reflexive property of congruence is that you'll have a segment is congruent to itself. It has the same length and it's the same shape. So that's what this represents, is that a segment is congruent to itself, and then we can use that same notion and say that an angle, in this case angle D, is congruent to itself. Okay? And then we've got the symmetric property of congruence. And again, this talks about relationships between objects that we know are congruent. So if we've got a segment that is congruent to another segment, then we can go the other direction and say the second segment is congruent to the first segment. Now this becomes important because if things aren't lined up orderly and we want to do an operation, let's say with objects, I know this is going to sound weird, we need to make sure that math that we're doing on the left is all the things are lined up underneath it. For example, if I wanted to get rid of an angle's measurement for some reason. Now, once I talk about measurements, I'm going to use that definition of congruence because any two things that are congruent, their measures are equal. And again, we'll get into that. Don't panic yet. If I wanted to subtract the measure of angle D from the left side and the right side, but the measure of angle D didn't show up on the left side, and that's the side I want to get stuff rid of, I can go ahead and rearrange my equation so that what I need to get rid of comes from the proper side. And again, that's probably not making a lot of sense, and I apologize. Again, I will demonstrate that in examples when we get there. And then we have the transitive property of congruence. So notice that if I want to use substitution, transitive property of congruence, substitution only works in equality situations. Transitive, on the other hand, both is a property of equality and a property of congruence. So if I have something that looks like I want to do substitution and I have congruent symbols, then the only option I have is the transitive property. And it says, and we have a couple versions of it, if segment DE is congruent to segment FG, and so we have two hypotheses that have to be true. Segment FG is congruent to segment JK. Then, because I have that overlap of segment FG, I can say segment DE is congruent to segment JK. Excuse me. And then we can also say this is true about angles. So if angle D is congruent to angle E and angle E is congruent to angle F, then angle D is congruent to angle F, because we have that overlap of angle E. Okay, so on the last slide, what I'm going to do is show you that properties can be used in proofs. So here's the scary bit. You guys are going to be taking a quiz on Chapter 2 shortly, and you're going to be asked to do a proof. But the nice thing is, I'm going to be kind to you on this first one. I am now going to only, on this particular quiz, the proof is going to be solely an algebraic proof. So you should have a lot of familiarity with this. So directions are going to say solve 3x equals 6 minus 1/2 x, and justify each step. And we actually could have had you do this last year with all the properties that you've learned. So first, let me introduce to you a common style for doing proofs, and that's called a two-column proof. So the reason why they call it a two-column proof, because it literally is two columns. We have S, which stands for statement. Okay, so that's we start with what we were told in the problem, and then we do what our math is. Okay, and again, let me go over that as I go. An R, and that represents the reason. So for every statement you make, you need to give me a reason why you can make that statement. So protocol when we're doing proofs is we number our statement and corresponding reason with the same number. So we start with what we were given, 3x equals 6 minus 1/2 x. And our reason we can state that is because it was given. So pretty much every single proof starts exactly that way. You take the hypothesis or the given information, you put it in as your first step, and you say given. Okay, some people like to split them up. So then you need to ask yourself, okay, what could I do now? And here comes the hard thing about proofs. There's not exactly one way to do them. There's a lot of leeway. For example, on this one, I don't like dealing with fractions. So me personally, I'm going to most likely multiply everything by 2 to get the fractions to go away. Some people might decide to get the x's together and that they would add 1/2 x to both sides. The actual order of the steps is kind of free-flowing, except if you need prior information to write your step. My multiplication step, my addition step, the answer I get does not affect doing the next operation, so that's why I have a little bit more freedom in these. So on this one, I'm going to multiply everything by 2, but remember what we did in algebra? We showed multiplying by 2. So I'm going to show you in green that you would, in your head, be doing this. Multiply by 2, multiply by 2, multiply by 2. But in reality, in geometry, you show me the result of doing that step. So you just would write 6x equals 12 minus x. Now I give my justification, my reason for why I was allowed to do that, and I say multiplication property of equality. And that's how I do my abbreviation. So I don't write out all the words. Some people use a multiplication symbol, and that's fine too. Alright, next, what do I want to do? I want to get all my variables together on the left. In order to do that, I would need to, going back, I'm showing you, you do not need to show this, I would add x to both sides. Now again, in geometry, we don't show the green parts, we only show the results of the green parts. So by adding x to both sides, now my equation is 7x equals 12. And again, what allowed me to get 7x equals 12 is the addition property of equality. And then lastly, I want to get x completely alone. So I have two options of doing this. I can divide both sides by 7, or I can multiply both sides by the reciprocal 1/7. And it really is dependent upon you what you want to do. Me personally, I'm going to use division. And so if I was doing this on an actual algebra homework, I would be dividing both sides by 7. But remember, green doesn't show up in a geometry proof. The result of the green shows up. So I have 12 plus 7, or 12, x equals 12 over 7. And that is division property of equality. Okay? So again, the green steps, and I'm going to go back and be a little tricky here, the green steps are not seen. Okay? They are not seen. Not in geometry. Okay? So properties are used in proofs, as we said above, but properties help to deduce, and we'll talk about that word later, an answer. So how do we get to our answer? We deduce it step by step. All right, have fun with this.